Hello, good evening, all. So, welcome to this final uh, session for this course, final problem solving session for this vibrations course. So, yeah. So, what I was planning today to discuss was like, so we can either discuss some sample problems. So, I have actually picked up some sample problems related to the course content for like throughout the all the weeks, and then uh, we could either uh, so we can actually either discuss those sample problems, or like we can go through them. Sorry about that. So yeah, so what I was planning that we can actually we can actually go through some of those sample problems that I picked up, or if you have any questions of your own, any problems that you wanted me to discuss, so we can take up those as well. So I think, yeah, so we can get started. So so let me know whether like, so do you have any particular questions or problems that you wanted me to discuss? Yeah, Mr. Amit, please.
Sir, can you access assignment number 2?
Assignment number two. Okay. Yeah. Okay. Just a minute. Yeah. So I'm logging into that. So I'm sharing my screen now. So just let me know whether you are able to see my screen.
Yes,
So
sir, visible, sir.
yeah. So I have opened up the week two assignment. Yeah.
Sir, I have query regarding question number 5 of this assignment.
Okay.
I am not saying to solve it again, but I am a small query which may be relevant to other problem also, sir. If you look this problem, sir, we have two spring and one mass, sir, here.
Right.
Okay, sir, I have seen the solution also and we have discussed it earlier also. But see, if I try to problem with like that, that there is a two spring forces M1, X1, M2, X2, and there is one inertia force MX double dot.
Mm-hmm. Right.
And if I make a force balance equation, sir, so I will not get the correct answer, sir. But I want to know that if I try this way, what wrong I am doing by doing so, sir.
Uh,
Instead of taking moments or using the energy method,
mm-hmm.
just I take the three forces in balance: the first spring mass, the first spring force, the second spring force, and the third is your inertia force, sir. So where did I went wrong, sir?
I actually still didn't get your question. So when you say moments and like method solving by using forces, so I actually didn't get what exactly you were trying to say.
Sir,
Can you?
solution I already know for this problem, sir.
Uh-huh.
Just I want to know that if I try the same problem
Right.
by writing the force balance equation, because
Yes.
there are two springs, so there will be two spring forces acting upwards.
Right.
If I give a small deflection to the rod, sir,
Right. Right.
and there is a third force which will be the inertia force, mx double dot,
Mm-hmm.
and then I add them by vector addition, k1 x1 plus k2 x2 plus mx double dot is equal to 0, and then I will use the formula that x is equal to l theta.
No, no. Just
So
that will.
where did I, yeah, so I want to know ki where I am going wrong, sir, here.
Yeah, so first of all, yeah, I got your question now. So okay, so first of all, yeah, so all these methods of solving, they are like uh, equivalent, so but like they will lead to the same answer, but uh, there may be like some method may be slightly simpler, or in that sense, or more convenient or simpler for that problem. So generally for these kind of problems, we tend to use these movement based methods. But yes, you can also derive the equations of motion using the force balance method. Like now coming to your sorry, so coming to your question. So now here you mentioned about considering the spring force yeah, so that is the and gravity. So that is the only I mean you can say external force acting. Now if you draw the free body diagram of this rod, so let me just take the help of the Jamboard. So I am also sharing my screen now. Jamboard screen. So are you able to see the Jamboard screen?
Yes, sir.
Okay. Yeah. So what here, like what we have is this system, right? So okay. Now, so if you draw the free body diagram of this rod with that mass, so what all forces will be acting onto it? So one will be basically weight acting at the center of mass. So which is like we neglect
Sir,
it. Uh,
yes, sir, because it is massless.
no, not massless. So if the rod is massless, that is okay. That and but there is also a point mass at the end, right? So there is also a point mass attached at the end. So this one. So we can actually consider gravity here, but it is not actually playing part in the dynamics, because it is just causing a static deflection, because the magnitude of the force will not vary, magnitude and the direction of
Yes,
the
sir.
force will not
Yes,
vary,
sir.
so it is just going to
Yes,
cause a static deflection. So then
yes, sir.
therefore we set the uh, when that's why every time when we solve, so let us say if we x is the measure, like the variable which measures the displacement of that mass, then what we generally choose is that x is with respect to the equilibrium position. So then in that case we do not have to consider the weight, because then we have already accounted
Yes, sir.
for the static deflection in that case, right? Now the next thing is the spring force. So let me just draw the, so let us say this is the k1 k1 delta 1 is, let us say, this spring force, and k2 delta 2, let us say, for the spring. Yeah. Now are these the only uh, net external forces acting on this rod? Are you sure? So are there any other forces also acting on this rod?
Sir, there may be reaction force at the fixed end, sir.
Yeah, exactly. So there will be a reaction force at this. So let us call it as some Fy, Fx. So we can resolve it in, let us say, because we are considering it in two dimensions. So we will assume two forces Fx and Fy for this support reactions. And then, so any other dynamic forces that you can think of? That's all right. So these are the only net external dynamic forces that are acting here. So now we apply the Newton's second law. So then we can basically get the uh, equation of basically, let us say mx double dot is equal to sum of net external forces. So like k1 delta 1 plus k2 delta 2 plus, let us say, Fy. Jamboard is not visible, is it? Oh, okay.
No, sir.
Okay, okay. So now is it visible?
Yes, sir.
Ah, okay, fine. So then, so like k1 delta 1 plus k2 delta 2, these are the two spring forces, and then Fy is the force F, like in y direction. So these, like, or x direction, for that matter, let us say if we are considering this as y direction, so then I will say this is y and x. So let us, like, now if we, so then we have to write this as y double dot now, and if we consider x as the displacement of this mass in x direction, so for small oscillations we will actually neglect this displacement in x direction, because it is like largely moving in the only in the vertical direction. So the movement in x direction, so there will be actually movement in x direction, but it will be very small as compared to the movement in y direction, because of the, let us say, if the like the angle of oscillations is like very small. So then we can, like, let us say, so if this is, let us say, some L1 and this distance, let us say, is L2. So then delta 1 we can approximately say that it is L1 theta, and delta 2 is, let us say, L2 theta. So that is the like approximate this thing. So then now then we can write the equation of motion in y direction. Now and x direction, so we assume it to be negligible. So then we can neglect the equation of motion in the x direction. Now now to solve for, like, Fy, now to, we do not know the expression of Fy as such directly, so then we need one more equation to kind of eliminate that. So for that we can actually use now the moment type equation, or so. Yeah, so if we can actually just take moment about the hinge or something.
Uh, Sir, actually, I just want to know that if we do the problem this way, will it be okay? Because further I can solve it, sir. Just I
No,
want
no.
to know that if I apply this method.
See, if you cannot just leave like this, my double dot is something, this thing plus Fy something, k1 delta 1 plus k2 delta 2 plus Fy. So you cannot leave it. I mean, you can leave it at that point, but it will not take you any further. Because
Yes,
it,
sir. I
yeah.
require one more equations.
So we need one more equation to actually know Fy in terms of other things, or we can just take the moment about the hinge. Uh, so now how do we know this Fy in terms of other.
But sir, if we take the moment about hinge, sir, both fx and fy will be zero, sir.
So there will be no moment of Fx and Fy. It will not be
Yes, sir.
Fx and Fy will not be zero, but moments about of those forces will be zero.
Yes, sir. Moment,
So
sir.
then it is much easier to write down the equation. But if we take, let us say, the moments about the center of mass of the rod or whatever this thing, then we will get the moments of this Fx, Fy or whatever, and then we can substitute that in this equation my double dot whatever Newton's second law, and then we will get actually the same equation of motion that we get
Okay, sir.
usually. Yeah, so that's what
Sir,
I.
actually, the solution provided by the in the respective TA, sir, he has taken inertia, moment of inertia of m also, sir, about hinge point, sir.
Yeah, it has to be taken because.
Yes, sir. That I couldn't understand actually, sir, because if we tried with using force equation only, sir,
Hmm.
then I will get different answer. And if I take the moment of inertia of m about O, the hinge point, sir, then I am getting the correct answer, sir. So I got little bit confused that why we are taking moment of inertia and why not, sir.
See, moment of inertia means, so if there is certain system, then mass is, let us say, distributed about that xy whatever xyz axis. So if there is some non-zero mass, that is, so even if there is, let us say, some point mass, so if there is some xyz axis and there is like one point mass placed somewhere, so if we are considering, like, let us say this is xyz axis, so if we are taking, let us say, the moment of inertia about the z axis, so then we need to account for the inertia of this object by taking basically the, let us say, because this is like a point mass, and let us say L is the distance from the z axis, so then the moment of inertia about the z axis will actually be ml square because it is a point mass. So one has to account for the mass distribution by, like, using the moment of inertia. We have to consider that for that. uh, Now if we kind of solve for I mean, so if you solve for this thing, so if we take the moment of inertia of this point mass about its own center of mass, so it will be actually zero. But you can say that I mean, so basically, wherever we place the axis about which we are taking the moments, and if there is a point mass which is present away from that axis, so one has to account for the moment of inertia of that point mass. If the rod is massless, so then we don't need to account for the moment of inertia of that rod. Um, but yes, so even in this problem, so if you use Newton's second law, so you cannot solve the problem simply by only using the Newton's second law. So you also need to write down a moment equation because there is a, so this problem involves translation as well as rotation. So it is a combined translation and rotation problem. So you have to bring up the uh, the uh, moments, or like equation of moments in somewhere. So, so for getting only the equation of motion in y direction, it may be just sufficient to take the moments about the hinge point. That may just be convenient and easy. But if you want to solve it by, let us say, the Newton's second law, uh, first write down the force equation, and then you can write down the equation of like moments about the center of mass of the rod, let us say, or center of mass of the rod plus that point mass combined system. So if the rod itself is massless, so then the center of mass will be exactly same as the center of mass of that point mass. So and then we let us say if we take the moments about that point, so then we will get an expression of fx or fy like in terms of the so we will get the expression of this force fx and fy in terms of the delta 1 delta 2 or whatever, and then we can substitute it and get the same equation of motion like that.
Okay, sir.
Any other question? Anyone else had any other specific problem or any question that you wanted to discuss? Okay. Anyone else had any question? So if not, then we can just start with the problems, set of problems that I had planned to solve. So those will be like related to content of almost most of the weeks that like or almost the entire course that we have covered so far. So we can so shall we start with that?
Yes, sir.
Sure, sir.
Yeah. So then and I also had planned to discuss some examples using MATLAB. So how you can use MATLAB to solve some simple vibration problems like related to the content that we have discussed. So yeah, so we can also discuss that if you are interested. Okay, so let's start with the uh, set of problems that we had planned to discuss. So yeah, so this is the first problem. So a harmonic motion has an amplitude of 0.05 meters and a frequency of 16 hertz. What is its time period, maximum velocity, and maximum acceleration?
Sir, your screen is not visible.
Oh, sorry. I'm sorry. I think I forgot to share my screen. Yeah. Okay, sir. So I have shared my screen now. So is it visible now?
Yes, sir.
Yes, sir.
Okay. Yeah. Yeah. Thanks for letting me know. So this is the first problem. So harmonic motion has an amplitude of 0.05 meters and a frequency of 16 hertz. What is the period, maximum velocity, and maximum acceleration? So this is just a simple problem where we know that a harmonic motion, so it has an amplitude of 0.05 meters, and so sine omega t plus phi. So omega is the frequency. So it is given that frequency is 16 hertz. So omega will be 2 pi f. So which is 32 pi radians per second. So the velocity will be x dot. So which is 0.05 omega cos. omega t plus phi. X double dot will be minus point. So now the maximum velocity will be 0.05 into omega, and the maximum acceleration magnitude will be 0.05 omega square. So omega we know already that it is 32 pi. So that's like how we can solve this problem. So we need not solve it numerically. So conceptually, this is like enough to discuss for now. So any questions?
No, sir.
Okay. Yeah. So yeah. So this is one more problem which was actually appeared in some GATE exam. So I just picked up that. So there is like, let us say, spring mass damper kind of system, and it's given that the free vibration amplitude reduces from 8 mm to 1.5 mm in 3 cycles. Then we have to find out what is the damping ratio of the system. Now, like if one can actually memorize formulae and then try to write like directly use those, but let us say for person like me, it's like I do not find it easy to memorize formulae. So then, how do you think we can solve this?
Sir, there is a direct formula that 1 by n ln xn by ln x0 by xn.
Yeah, yeah, I know. That's what I told you, right? So if there is, let us say, some direct formula, but if like you can always use that. But let us say if I don't know or don't remember that formula, so then how you can derive the same thing if you don't know the or don't remember the formula. So any idea how to solve that?
Sir, assuming small x is equal to capital X e raised to power minus, starting from the basic formula, the
Right, right. Yeah, so
solution of the
correct, correct. Right. So if we don't remember the formula like of this system, like this is mx double dot plus cx dot plus kx equal to 0. So this system, like if we don't remember what is the the formula of whatever this so then we actually can, as you mentioned rightly, so we can just substitute that some e to the power x is e to the power some st or lambda t or whatever, and then substitute it in the differential equation and then solve the characteristic equation, and from the characteristic equation we get the roots. Yeah, so the first of all, the fact that it is given that there is a vibration, so that means that and there is damping present in the system, so that means that the system is under damped. So then you actually don't need to do this also. So then you can just pick up that particular form of that solution. So what is the, like, let us say, typical type of response? Uh,
S1t plus
so I'm just trying to basically write down like from memory. I'm just trying to kind of write down what is the
e,
general
e raised
form.
to power S1t, sir.
Yeah, so we will get some a raised to zeta omega and t into sine of
Sir, it will be
zeta.
minus zeta. E raised to power minus zeta.
Right. Minus zeta omega and t into sine of uh,
Omega and d. Omega and d.
so yeah, so damped natural frequency, let us say omega
Damn
d,
natural frequency.
yeah, omega d t plus pi. So, right, so this is the general form of the equation, right? Yeah, so there was a question, so in the chat. So, sir, will you please upload this video in YouTube? Yes, I will upload the YouTube in like video in YouTube. Yeah. So then, yeah. So let us say if we okay, so people, so the person joined the meeting just to ask that whether this video will be uploaded on YouTube. Okay, interesting. Yeah, so the response, nature of the response will be something like this, right? So, so let us say if we are considering like a particular time instant, let us say some t1, and in the question it is asked like the amplitude let us say it reduces from 8 mm to 1.5 mm in 3 cycles. So so after one cycle it will be here, and after another one cycle it will be here, and again after another cycle it will be here. So it will be like this: t2, t3, and t4. Let's see. So basically t2 is equal to some like this t1 plus the time period, and similarly subsequently t3 is also t1 plus two time periods, t4 is t1 plus three time periods basically. So 3 cycles, so that's why three time periods. So so we can basically write down, let us say if so what let us say this x1 is the displacement over here and x4 is the displacement here, and let us say this was 8 and this is let us say 1.5. So then we can just write down that using the general form of the equation. So x1 is a e raised to minus zeta omega n t1 sine omega d t1 plus phi, and then x4 will be a e to the power minus zeta omega n t4. So we have already written that t4 is t1 plus 3 time periods, and sine of omega d t4 plus phi, right? So t4 omega t4 means again so omega d t1 plus omega d into 3 time periods plus phi, right? So because t4 is t1 plus 3 time periods, and then we know that x1, so this is 8 and this is let x4 is 1.5, let us say, and there are 3 cycles, right? So then we take x1 by x4 is 8 by 1.5. So then we get t1 is can be anything, it is any arbitrary point. So it can be any arbitrary point, and then like we measure the amplitude at any
Okay, sir.
yeah, any arbitrary point, and then take 3 cycles after that. So
But sir, it will change the values because this 1.5 and this 8 are the values at particular time period, sir.
So they are 3 cycles apart, right? So it can be, so we don't know the specific where it started from, what is the
Okay,
initial amplitude, and
okay,
so
sir. They need not be the first three cycles.
need not be. So it is not given
Okay, sir.
anything, there is no information given on that, and we need not even bother about that because it is just like in a certain vibration signature. It is like for those 3 cycles, it reduces from, like, let us say it starts from 8 and then after 3 cycles it goes to 1.5,
Yes, sir.
right? So yeah, so then if we divide now, we have like this a and a will cancel, and then e to the power minus zeta omega n into t1 plus 3t. So if we divide x1 by x4, then what we will get in the numerator is e to the power zeta omega n into 3 time periods t, and sine omega d t1 plus phi, and sine omega d t1 plus this omega d into 3t. So what is t? Time period is 2 pi by omega d, right? So then 3t into omega d will be basically 2 pi into 3 times. So it is basically integer multiple of 2 pi, or so sine uh, 2 pi n plus theta is same as sine theta. So then that's why value of this and this will actually be exactly the same, because it is exactly at that after 3 cycles. So then this is the only term that we will get. So the ratio of this, so e to the power 3 zeta omega n t. So x1 by x4, sorry, okay. So t is basically 2 pi by omega d, and omega d is omega n into root of 1 minus zeta square, right? So omega n will get cancelled. So it will be basically 6 pi zeta, uh, sorry, so exponential or e to the power 6 pi zeta by root of 1 minus zeta square. And if we kind of take that approximation that, zeta is much smaller than 1, so then we can just simply neglect this term. But if we want to keep it, we can always keep it, and the only thing it is like, it will just make our solution slightly more complicated. So then we can take the logarithm of both sides, and then, as you know, that if you are familiar with the usual procedure, so that log of whatever that you were saying, so that same thing we can use. So you will get basically the same formula that you were saying. So yeah, 0.088. Yeah, so it may be, yeah, I haven't tried, but yeah, I think someone also already got, yeah, so Prashant sir also got the same answer. So I think, yeah, that must be the answer. So yeah, so you don't always need to memorize formula. So you can also, if you just know the general nature of the solution, so you can also derive the formula from this using that approach also. Okay, so any doubts till now?
Sir, actually remembering this formula that this delta is equal to 2 pi zeta upon 1 minus zeta is much easier than remembering x is equal to x e raised to power minus zeta omega nt.
Yeah, it may be. You can
Yeah,
like,
that is the issue, sir.
yeah, you can.
Because
Yeah, for I'm just telling you from my point of view. So I generally find it very difficult to remember formula. But if one is able to remember, then it's well and good. Like, there is no need to go
yes,
through this process. Yeah.
yes, sir. Yes,
But when you need apply formula, when you memorize and apply formula, we have to be careful. Uh, like for like what situation you are applying and what was the formula derived for. So just be careful about that. So yeah, so let's move to the next problem. So I have another question like yeah, this is a very simple problem. So it's about like there are two pairs of it's a pair of springs, each having a given spring constant, and the time required to complete 10 oscillations is how many seconds? So what will be the natural frequency here? So it will be root of
2k, 2, 2k by m.
right. So it will be 2k by m because the springs are in parallel. So which is 2000 by 20. So which is 10 radians per second, right? So the time period will be 2 pi by 10, and so the time required for 10 oscillations is 10 time periods. So it is same as 2 pi, which is 6.28. That makes sense? Okay. Yeah. So let's move to the next problem. So just let me know whether have we discussed this problem already or have we haven't. I don't remember. No, right? Yeah. So I don't remember discussing this, but I just picked it up. Yeah. So this is about so machine is subjected to an external force. Magnitude of the dynamic force transmitted from each mount to the ground. So how the dynamic force is being transmitted to the ground? It is through the spring forces, right? So we can just write down the equation of motion. So So this is the equation of motion for this kind of a system, but here we don't have any damping. So we will just get, because there are two springs, so we will get two forces. So this will be basically 2kx. So then this is the equation of motion. Now to solve this equation, so there will be like two parts, or to the like to the, so the solution will have two parts, right? So one will be the transient one, which is basically the free vibrations, and another will be the particular solution, or this steady state amplitude basically. Now because there is no damping present in the system, the transient part or the free vibrations part will always be present in the total response. So we need to consider that, we cannot just ignore that. So the free vibration response we can find out using this differential equation. So mx double dot plus 2kx equal to 0. So the solution to this will be the complementary function or the free vibration response. And then, so because f is some, let us say f naught cos omega t, so then the steady state response will mirror this. So let us we assume the solution of the form a cos omega t plus b sin omega t as the particular solution, and then substitute it in this differential equation. So x double dot will be, so x double dot will be this, because we have assumed a sinusoidal kind of a solution. And now we can substitute this in the differential equation. So mxp double dot plus 2kx is equal to f, so which is 50 cos 5. Omega is known, so let us say, so omega is equal to 5 is already known. So now then we can substitute this in the differential equation and then compare the coefficients. So 2k minus m omega square is equal to 50, and the coefficient of b, which is so there is no sign term, so then that will be 0, so then b will be 0. And then we can find out the value of the a coefficient of a, which is 50 upon 2k minus m omega square. So that will be the uh, coefficient of this a. So a will be 50 by 2k minus m omega square. B is 0. So then we found out the particular solution. So omega is already known, K is also known. So then M is also known. So then we basically know A. And similarly, because it's a simple single degree of freedom system, which is undamped. So then we know the free vibration response also. So the solution for free vibration will be similar. So let us say C cos omega nt plus D sin omega nt. Yeah. So now the uh, coefficient C and D will depend on basically the initial conditions now. So let us call that as xh. So depending on what is the initial condition, we will get the values of the uh, C and D coefficients depending on, let us say, what is the initial displacement x0 and x dot 0, the initial velocity. So depending on that, we will get these values of C and D. And now we know what is omega n. So omega n is basically the natural frequency without any external force applied. So for free vibrations, so then so omega n is root 2k by m, right? So that is the natural frequency. So based on the initial conditions, we get the uh, values of C and D. Now, but there are no initial conditions given here. So then we can, let us say, in this case, we can assume it to be 0. Then we can assume that C and D, capital C and capital D will also be 0 because there is no initial condition or no initial motion. So then we can just go with that. So then there will be no, so the xh will actually be 0. So there will be no transient vibrations because let us say our initial displacement and initial velocity were 0. So then the solution will be same as the particular one for this case. Then so the forces will be basically so 2kx is the total spring force which is being transmitted to the ground, and we know that x is now the same as this a sin a cos omega t, right? So b is 0, and we have found out what is the value of a. So the net force will be 2kx, where x is the steady state amplitude. So this is the steady state amplitude, basically the 2k into steady state amplitude of the displacement. So this will give you the value of the total dynamic force that is being transferred through the springs to the ground. So what was the natural frequency here? So omega is given as 5. So 2k minus m omega square. So this will be the magnitude of the static force, or magnitude of the steady state force that is acting. So this will be, so I got the answer as 66.67 Newton. So this is the magnitude of the static force that we, magnitude of the, not static force, but the excitation force that is being transmitted to the ground. So is it okay?
Sir, what is meant by XH? What is the full form of XH?
Yeah, so this is the solution to the homogeneous differential equation, which is mx double dot plus that, this like the right hand side is to be like 0. So so the solution to this differential equation mx double dot plus 2x is equal to 2kx is equal to 0. So that is called as xh. Let us say homogeneous solution to the homogeneous differential equation, and that is represents the free vibrations.
Sir, don't we call it XP, sir?
XP is the particular solution which follows the excitation, and that is the particular solution. Uh, so if you want to go with some other notation, XP or some X something whatever, that is fine, but make sure that you kind
Okay,
of combine.
okay, sir.
Yeah.
Sir, I have tried this question in another way, sir,
Okay.
uh, by finding the transmittability first, sir,
Okay.
because it is equal to Ft by F0.
Okay.
And we know there is zeta is equal to 0. So the formula for transmissibility becomes 1 upon under root 1 minus r square plus 2 zeta r whole square, sir.
Right, but there is no zeta here, right?
So I will put it 0, sir.
Zero, huh? Right. So do you get the same
So,
answer?
sir, not exactly, sir. I am getting about 57 Newton, sir.
57. Okay. Okay. It should actually be the same, right? Uh, yeah. So for transmissibility, you would have substituted. Uh, so Ft by F0, as you said. So it is. Yeah. So what was the formula? So can you just tell me? I don't remember. I don't remember it actually.
1 upon 1 minus r square.
1 upon 1 minus r square. So this is
Yes,
using
sir.
that zeta equal to 0. So is it square root or not square root?
Sir, there is no square root, sir.
Okay, no square root. Okay, fine. 1 upon 1 minus r square. So what is r? R is basically omega by omega n, right?
Yes, frequency ratio.
Okay. And what is omega n? Omega n is root of
14.14, sir.
2k by m, right? So, okay. And omega is 5, right?
F0 is 50 Newton, sir.
F0 is 50 Newton, right? So it will be basically 50 upon. So omega n comes out to be.
No, sir. F0 is 50, sir.
Yeah, F0 is 50, that I understood. So Ft will be 50 by 1 upon 1
Okay,
1
okay, sir. Okay.
upon 1 minus r square. So
Omega n is 14.14, sir.
14.14, okay. 14.14. So R is 2.828. So, oh, not sorry, not. So 5 by 14.14.
Sir, r square is 8 only, sir.
No, R is omega by omega n, right? So omega n is greater than that. So 5 by 14 something, that 14.14, right? So that is R, right?
Yes, sir. You are getting the same answer, sir.
So R is something like 1 minus 5 by 14.14.
So it will be omega by omega n, sir.
Yeah, it will be omega by omega n only. So 5 by 14 something. R is omega by omega n, right? So it will be omega 5 by 14, right?
0.125, sir.
Yeah, 1 minus 0.125 approximately. So it is uh, so approximately
57 is the
so
answer.
it is 57.
Yes, sir.
This is slightly different.
Quite different, sir.
Hmm. Okay. But what I did is uh, okay. So we get R equal to omega by omega n is 0.5. Okay. Okay, so let me check once again. So what exactly? But I think these methods are equivalent. Like there is nothing fundamentally different in whatever that we are doing. So we should actually get the same answer. So yeah. So omega n will actually be 10 only, right? So yeah, so omega by omega n will be actually zero point 0.5 only, right? So yeah, R is equal to zero point 0.5 only. So yeah, so it is because omega n is actually root of 2k by m. So yeah, so omega n is actually 10 and omega is 5. So R will be actually zero point 0.5 only. And yeah, so yeah, 1 upon 1 minus 1 by R square, 1 upon 1. So Ft will be 50 into 4 by 3. So 200 by 3, which actually comes out to be 66.67. Yeah. So yeah, so that omega n is sorry, yeah, omega n is 14. That is not correct actually. So it is only 10. Should be 10 actually.
Sir, what is the value of K here, sir?
K is 10 kilonewton per meter, and because there are two springs, so it in parallel, So then it becomes 2k by m. So so it's not 14 actually, so it's 10.
Okay, sir.
Okay. So yeah. Yeah, so this one was one example which I had planned to discuss using MATLAB. So maybe we will actually just keep it for later. First, let us cover uh, the basic problems that we need to do by hand. Yeah, so this was related to a multi-degree of freedom system. So this was actually part of the problems which I had planned to solve for the two degree of freedom systems, but this was not solved in the session. So we can actually discuss this problem right now. Yeah, so this system has like a two masses. So one is inside this kind of a tube, and there are two springs K1 and K2, and then there is like another mass M2 which is attached like a pendulum. So now we can consider, so it's a two degree of freedom system, right? So if we consider that that uh, this length L, let us say, is fixed, then we can consider, so that will become a two degree of freedom system. So the degrees of freedom can either be x1 and x2, or it can be x1 and theta. So right, we can derive the equations of motion using either of them, but the natural frequency of the system will still remain the same. So it will not change based on the choice of coordinates as such. So it will just make the derivation either way. So what we can do is, like, we can consider, like, we'll try either problem A or B, and then we'll derive the natural frequencies of vibration of the system C. So in the interest of time, we can just try either part A or B. So let us choose part A. So then you can try solving using B on your own, and then we can derive the natural frequencies of vibration for this system. So the first step is to draw the free body diagram. So then here, because we have two springs, so and both are like acting in an opposite way. So when we move the mass to one side, then one spring will be stressed and the other will be compressed. So the free body diagram for the mass m1. So x1 is like this. Because the spring K2 is being compressed, and then the spring K1 is being stretched. And there will be one more force, which is basically the tension in the rod. So let us call this force as T, and this will be acting at an angle theta with respect to the vertical. Similarly, now for the pendulum mass M2, now here we cannot neglect the mass M2, the gravity force for like M2G, because that gravity itself becomes a dynamic force in case of a pendulum, right? So gravity itself causes the oscillations of the pendulum. So then we cannot neglect the force of gravity in this case for a pendulum. So one has to be careful when you can just simply, you may end up with nothing if you neglect gravity for a pendulum. So yeah, so we are done with the free body diagrams, right? So any other force that is left? None, right? So now we can write down the equation of motion for both of these systems. So now what is the displacement of mass uh, M2? So it is so x2, we can write it in terms of x1 and theta as x1 plus what?
L sin theta.
Right. So it will be x2 is equal to x1 plus L sin theta. Correct. So then, so if we derive the equation of motion in terms of x1 and theta, we can just simply translate that same equation into x2 by using this substitution. So, so now let us write down the equations of motion. So m1 x1 double dot. So so that will be sum of the net external forces. So T cos theta will be acting downwards, and there will be, let us say, a normal reaction which will resist this vertical component of the tension. But we are considered like we are bothered of the motions along x1 direction only. So then we will only write down the equation of motion along that x1 direction. So the component of the tension T acting along the direction of x1 will be T sine theta, right? And the rest of the spring forces, so K1 plus K2 into, sorry, x1. And then the other equation of motion will be m2 x2 double dot is equal to, so x2 double dot, x2 is like this, and there will be also another coordinate, let us call it as y2. So in the y direction, is equal to T cos theta minus M2 G. So now geometrically, what is this displacement y2? So it will be L cos theta, right? So y2 will be same as L cos theta. Then so x2 double dot will be x1 double dot minus so to solve this equation, like we also need to consider these equations and like differentiate them with respect to time. So that is also important. So x2 is x1 plus now you may be thinking that will there be such a difficult or such a lengthy question in the exam or not? So the answer may be that it may actually be you may not actually come across such a lengthy question, but at the end of the day it is like important to understand that so if you encounter any problem in dynamics, so you have to just follow the same basic steps. So basically define the coordinate system, draw the free body diagram, then write down the relations between the coordinates if any. So like that in this question, so we have this x2 and x1 and y2 or whatever that so those are the different coordinates. So here x2 and y2 are actually not independent because the length is fixed. So then x2 and y2 are not actually independent coordinates. And then once we get the coordinates and then draw the free body diagram, so then we can just write down the equations of motion and then use it to derive the so once we get the equations of motion, then we have to set up the eigenvalue problem to get the natural frequencies. So this is the general usual process of deriving the natural frequencies. So that will remain the same no matter how complicated or big the system is. So it will be always the same process. So one has to just define the geometry and coordinate systems like carefully and then just follow the algebra, and the algebra will set everything right if you draw the free body diagram correctly and write down the equations of motion correctly, so then the everything will come into its place correctly. Now we have to differentiate x2 to get x2 dot. So I am writing down that. Now so x1 is also varying with time and theta is also varying with time. So derivative of L sin theta will be L cos theta into derivative of theta with respect to time. So L cos theta into theta dot. Now further if you want to get x2 double dot, so that will be x1 double dot plus L cos theta. So now we can use the chain rule of differentiation here. So here L is a constant, so that will not vary with time. Then So the next term, so L cos theta into theta double dot minus L sin theta. So then again, so derivative of L cos theta is L minus L sin theta into derivative of theta with respect to time, and there is already a theta dot term here, so it will be basically theta dot square. Similarly, y2 dot will be minus L sin theta theta dot, and y2 double dot will be minus L cos theta into theta dot squared minus L cos L. So everyone is able to understand till this point of time, this point. Anyone has any doubts? So if you just need to just follow the algebra, like and like do the differentiation correctly. So if you just get basically are first able to get this, I mean this part correctly. So this is the most important. So if you get this correctly, then everything else will just follow from the geometry and everything. In the exam, yeah, they may ask only to opt the equation of motion. Yeah, possibly, possibly, but yeah, but still you generally need to, you can guess the terms, etc. like from the options also. Like if you are but confident, like if you are very clear and confident, then you can actually guess some terms and then see, make out which is the correct option from that. So but one needs to be still very careful uh, in that. So yeah, so you may not always have to go through the entire process of derivation. So from if you have options given, so then you can make out from the options like which one is likely to be the correct one.
Sir, in this question, why we are not considering the mass moment of inertia of the pendulum M2, sir?
No, we are not considering. What do you mean by we are not considering the mass moment of inertia?
Like M2 is actually rotating with the point of suspension.
Yes.
That means theta, theta double dot, like that, sir. So why the term I theta double dot is not appearing, sir, here?
No, because we are not considering any moments yet, right? So there is no moment equation written yet. So once, because that comes into picture only in case of like when you write down the equation of in terms of like when you consider the rotation. So here you are right that the mass M2 is actually undergoing rotation as well as translation both. So that's why we are writing two equations of motion, because it has motions along the two axes. So along x2 and as well as y2. So those two equations can be uh, combined, like so those two equations represent the translation plus rot, because So it can be either interpreted as like two independent motions in or two motions in if not independent, but uh, like motions in two directions and equations of motion along each individual direction. So that is equivalent to writing a moment equation. So if you so if you want to write down it as a moment equation, etc. So but you cannot choose this I mean point. So you cannot like choose this point like the center of mass of this m as a inertial frame because it is accelerating, right? So then if you want to write down the moment equation in terms of the of an like if you want to write down the moment in terms of an inertial frame of reference, so then you need to carefully choose that. So you can take the moment of forces about any point in the plane, but so you can choose it so that most of the forces pass through that point and there will be like zero moment of about that that force about that point, etc. So in this, in case of a static, like the when the pivot point of the pendulum is fixed, so then you can easily conveniently choose the pivot point as the point about which to take the moment. So for a pendulum we can derive the equations of motion using uh, that same taking moment about the pivot point and uh, so that can be one way of deriving the equations of motion for the pendulum. So the other way is using this so by the way, actually you can even for a simple pendulum you can also use the same method to kind of derive the equation of motion. It you will actually end up with the same equation. So for a pendulum, simple pendulum, so this tension and mg. So if you take like the moment of the force, so this mg, and if this is the so the moment of mg about the pivot point, let us say O. So mg into L mg into L sine theta. So that is the moment about this thing, uh, the pivot point O. So and this comes out to be in clockwise direction. So write it as minus. We write it as minus, and then so that is equal to moment of inertia about this point O into theta double dot. So now what is the moment of inertia about this point O? So if this rod is massless, then it will be m into L square minus mgl sine theta is equal to ml square theta double dot. So this comes out to be the same as, so if we now assume that sine theta is nearly equal to theta, then we end up with the same equation. So theta double dot plus g by L theta is equal to 0. So this is the simple pendulum equation of motion. So this is using that moment wala method. But now if we want to derive the same equation of motion using alternatively using the Newton's second law, we will actually end up with the same equation. So do you want to see how?
No, sir, I can do for this problem, sir. There is no problem.
Okay.
Using L sin theta, L cos theta, you mean, sir?
So again you will actually use the same thing like instead of this x2 y2. So now there will be no x1. The motion of the pivot is not there, right?
X1 will
So
be 0, sir.
so then x1 will be 0 So the x coordinate of the thing center of mass is basically fixed. So like this pivot point is fixed. So then x2 will be just only L sin theta and y2 will be same L cos theta. So and just differentiate it, then we will get actually the same equation of motion. So yeah, so if we come back to our original problem now, so now to get a simplified like so there will be only 2 degrees of freedom, so we have to combine these three equations of motion into two only because only two are independent actually. So we need to do some algebra to kind of substitute like some terms. So like for example, so y2 double dot is something and x2 double dot is something. So then we can use that to kind of eliminate one of the variables. So let us say if you want to eliminate t, so then we have to do some algebra to rearrange them and then we get just one equation out of these two. So these two. So let us say if we use x2 double dot is minus t sin theta by m2 and then put it into this equation or not this way actually. So what I meant was t is minus m2 x2 double dot by sin theta and then put this value of this then put this expression into this equation m2 y2 double dot thing. So we will be able to eliminate the variable t and x2 and y2 is already known in terms of x1 and theta. So we will get the second equation of motion and the first equation of motion will be so this one and the other one will be 2 after combining this into this. So it will be like a very, so you need to patiently do all that and so in the interest of time, so do you want to actually go through the entire derivation like algebra everything or you will do on your own? What do you think? So do you want me to go through the entire derivation process or like you can, yeah, so you want to do it on your own, right? So okay. So it's like it will be just become very lengthy and yeah, once you get, so you will get basically two like the equations of motion you will get in terms of so you will get two equations of motion and you can write it in terms of like in a matrix form. So to be able to write it in a matrix form, so if you actually make the assumption of that theta is small, only then you will be able to uh, write the equations in matrix form. So then sin theta is nearly equal to theta and cos theta is nearly equal to 1. So that assumption, so these things we can substitute So, but one should substitute these things only after deriving the equations of motion in the most general form without any assumption, and then you put the simplifying assumptions and then simplify it and write it in a more compact form using matrix notation, etc. And then once you get the equations of motion that way, you will be able to uh, solve the eigenvalue problem. So you will get a mass matrix and stiffness matrix, and so you basically need to solve this. So if m and k are the mass matrices and x is the vector, so we substitute x is equal to v into e to the power some lambda t, or if you want to just directly get the natural frequency, we can substitute it as I omega t, e raised to I omega t, and then we will get the matrix as k minus m omega square into x is 0. And for this equation to have a non-trivial solution, so we basically use this determinant of this matrix is 0. So using this we will get a equation like in terms of omega square. It will have the roots. So the roots will be basically the natural frequencies. So that's how you can solve for the natural frequencies. So so is it okay? Is it clear? Okay. Then I had some more problems. Yeah, so we can actually quickly discuss this one. So are you more interested in solving these kind of like these problems, or do you want me to skip the problem solving part and move to a MATLAB type examples, like considering like we have, if we have 10-15 minutes, do you prefer to? Okay, small questions. So I don't think I have small questions, but yeah, so we can maybe discuss like one or two questions. What is the? No, I actually don't have MCQs with me right now. I I don't have any. Okay, so there is one MCQ type question that I had. Okay, so this is related to like finding the natural frequency of this system. So here, yeah, so because it is rolling without slipping, so let's draw the free body diagram of this. So there is this disk and which is rolling without slipping. So if this is the center, now let us consider this x as the coordinate, and if we have stretched the spring and released, so let us say the spring is in tension. So this is the spring force. So let us say k delta, and is acting at a distance d, and so there will be the weight W, let us say. There will be a normal reaction, and so let us say the friction force is acting like this. Let us call it as friction force is F. So these will be the forces. So now one equation of motion that we can write as is the so in x, like if this is the x, positive x direction, so mx, so capital M is the mass of the disk, so mx double dot is minus k delta plus friction force in x direction. Then weight will be same, and normal reaction and weight will balance each other. And other equation can be moment about the center of mass. So this is the center of mass g, let us say. So moment of about the center of mass g into theta double dot. So if theta is the angle of rotation, so there will be two forces that will be providing the moment. So k delta will provide it in clockwise direction. So it will be k delta into d minus friction force into radius a, let us say whatever a, and friction force. So now we have to eliminate, let us say, the friction force. So for that, and like so this x and theta are two different variables, but they are not independent, right? Now it is given that the disk is rolling without slipping. So then what is the condition for uh, rolling without slipping? What will be the condition? So friction force cannot be always mu into W, because it will be mu into W only if it is slipping. Because at the point when friction force has actually reached the point at which the thing starts slipping. So do not be tempted to always replace friction by mu into normal reaction. So it will not be always the case that friction is mu into n. So it's, yeah, so in especially in these cases of rolling without slipping, you should not use this friction is mu into n directly. So rather you should actually consider the condition for rolling without slipping. So what is the, so if a cylinder is rolling without slipping, so let us say if this is the direction of theta and this is the direction of x in which it is traveling, and the radius is r, let us say. So what is the condition for rolling without slipping?
R theta more than x.
No, when it is rolling without slipping, then x is greater than, x is exactly equal to r theta. Now if it is slipping, then x can actually be greater than r theta. So for this rolling without slipping, so this is the condition that we invoke in this case. So here radius is given as a. So let's replace it as a. So then x double dot will become a theta double dot. So using this thing, we can now eliminate the friction force. And what is delta? So delta will be d sine theta actually, but for small oscillations we can call it as d theta only. And what is Ig? Ig is given as ma square by 2. So Ig theta double dot is equal to minus k delta into d. So minus kd square theta minus fa. So now if we multiply this whole equation by a, so we will get ma square theta double dot is equal to minus kad theta plus fa. And yeah, so then we can add up these two equations. So and then we will get 3 by 2 ma square theta double dot is equal to minus k into d square plus ad theta, and ff will be cancelled. So 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 then omega square will be equal to, so using the usual form of comparing that, so we will get So omega will be square root of this. So 2kd into a plus d into. So is it matching with any of the options? Oh, it's not matching with any of the options. Okay, so let me just check the derivation once. So, but yeah, broadly, this is the method that we should use to solve these kind of problems. So,
Sir, why you have taken polar moment of inertia here, sir?
polar moment of inertia I have taken because I have considered this moment equation, like moment about the center of mass for this rotating disk.
But that I want to say, why not mass moment of inertia here?
No, it is mass moment of inertia only. If I write it Ig, I mean, I just, it's like, I mean that mass moment of inertia itself, not area.
But the value you have put, I think, belong to polar moment of inertia.
Sorry.
Sir, can you show the question again, sir? Sir, this ma square by 2 is polar moment of inertia.
So polar moment of inertia of like mass moment of inertia. So it's same basically. The polar means basically about the axis perpendicular to the plane of that disk. So I mean, polar moment of inertia means just that, like nothing else as such. Like, so when I write it as Ig or whatever, so Ig means basically about the center of mass. So if whether I write it as J or I or whatever, so I mean basically the same thing, like the polar moment of inertia, same thing about the center of mass. So does it answer your question?
Sir, I will check. I will.
Okay,
I will check, sir. I have little bit confused between these two terms, sir.
okay. No, the mass moment of inertia and area. So polar moment of inertia term can be used like this, whatever you can say convention naming. It can be used for area moment of inertia, or you can use the same concept for mass moment of inertia also. It's like the same thing. You just need to specify whether you are talking about area moment of inertia or mass. So here it's mainly mass moment of inertia in this problem. So I found out what is the issue here. So basically, delta is actually a combination of the motion of the center of mass x plus this rotation about the center of mass, so which is d into theta. So which is a plus d into theta. Now if you substitute this delta, then we should get the options like one of the so it will be minus k a plus d whole square theta. Yeah. So this is the answer that we get. So is it correct now? Okay. I think yeah, now it is I think correct. So I still didn't get what exactly was your confusion regarding polar moment of inertia. So is your question resolved?
Sir, actually, when we study shafts,
Yeah,
we use the term like T by J is equal to n theta upon L, the famous formula for from strength of material, sir.
torsion. So then we
Okay,
are
and there we use the term polar moment of inertia,
correct, correct.
and sometimes we use mass moment of inertia. We usually donate by I only, sir. And polar moment of inertia we use J word only, J alphabet, sir.
So notation can vary from place to place, textbook to textbook. So things like it can be vary, but in terms of the context, like we can here we are talking about mainly mass moment of inertia. But for torsion, in that cases we are talking about stresses and all. So then there we are actually talking about area moment of inertia. Uh, so that can so the word polar moment of inertia actually means that about the axis perpendicular to the plane of it. So here it is a disk which is a planar object, so perpendicular to the plane, so it will be called as polar. But so you can say it is polar mass moment of inertia or polar area moment of inertia. So likewise, but if it is like in the plane of that, so that is like if you are talking about the moment of inertia in the plane of the disk. So then that is not called as polar moment of inertia. So that is called something else, right? So letter J generally it means whatever polar moment of inertia, but it is like mass for mass in case of this thing like in this particular problem. So yeah, so that's all that I had from my side. So thank you all of you for joining these problem solving sessions, and I hope all of these sessions were useful for you. So I think we it's already time now. So I think we can conclude our session for today. So should you have any quick questions before we conclude for today? Sure. Yeah. Thanks to all of you for joining these sessions. And yeah, I wish you all the best for your exams and whatever your future endeavors and careers are. So thank you so much for joining. Yeah, sure. Thank you. Thank you, sir. Um, so yeah, so if you still have any questions, so you can um like write like if you can email your questions to me if you still have anything else to discuss, and I can also share my uh, yeah, so this is my email ID. I have shared it in my chat. So you can write your question to like email your questions to me. So I'll try to answer those. So that's all that I had from my side. Thanks for attending and all the best. So good night. So we can conclude our sessions here now. Thank you. Good night. Yeah. Okay. Thanks. All the best.